All right, it's recording. So here we go. I moved on to 17A. That's what I said last week. For those, like I said, exercise 16E, if you're interested, you can have a look at that exercise. I will come back to it when we do kinematics. But at the moment, I'm working off your understanding of C, 16C, 16D, so what's average rate, to what's instantaneous rate of change. And then now I'm introducing you to chapter 17, first principles. Notice the questions are mixed here. So you got 17F that deals with limits. So I need to teach you what limits are, what's the purpose, and then combining those two understanding from 16C and 16D, I can then teach you first principles.
What happened to 16?
Yeah, so like I said, I will come back to that when we get to kinematics. Reason why I wanted to link it so that it's more relatable. So when you learn 16C, 16D, you can see how it links back to 17A. And then from there, I'm going to teach you all these derivative skills. And once you can then apply, we'll go back to 16E with kinematics. Okay, so at the moment, I'm teaching you more of a theory and then some basic skills from here on. But there's only, today, Wednesday, and I don't have you Friday. No, I do have you Friday because just the year 12s, they're doing the English exam. So it's okay. All right, here we go. 17A, first principles. It is not on the curriculum in the future, but I still think it's important to teach because it gives you an understanding of how or why derivatives work and what it is really. Okay, so this is the formula that I want you to copy down. So part of your notes, exercise 17A, if you've never seen first principles before, what I want you to copy down is this. So this is what I want you to copy down. And I will break that down so that you understand what it's actually asking. But first thing is you need to understand what that is. Once you understand what that is, then when I start describing the derivative, then it will make much more sense. Okay? Note the notation. It's little f with a dash on top, or f prime. F dash of x is how we read it. So I'm going to write it over here. This is read as f dash of x. Okay, so instead of saying f of x, it's now f dash of x. And that generally means that we're referring to the derivative. This is called first principles right here. This is called first principles. And it's very much, the purpose of it is, for those who have been practicing 16C and 16D, the purpose of a derivative is simply to find the gradient of the tangent line at one point. That's literally the purpose of this whole entire chapter. It comes to, and I'll keep reminding you that every time you find the derivative, I'll ask you, what are you doing? Okay, to remind you that all you're really doing at the end of the day, no matter what curve you get, you're looking for the gradient of a tangent line at that particular point. Okay, which links back to 16D, instantaneous rate of change. Okay, before you can do this, that's the theoretical component. Later on, you will not be using this formula over and over. You'll learn shortcuts, and that's where all the derivative rules come in. I'll teach you shortcuts on how to derive a curve that is a polynomial. I'll teach you rules that you can derive curves that are sine or circular functions. I will teach you for logarithmic curves or exponential curves. Each and every one of them follow this one principle to then come up with a shortcut or rule. And that's why you have to learn those rules. Okay, but they all come back to this one idea. Once you understand the idea, then you can apply yourself and then do applications. But without that, most students only learn how to derive. They don't know what it means. They just know how to derive. And then from there, they can't do applications. It's 2/3 of your course next year. Okay, so when you're doing applications, you can apply this derivative into all the functions you've learned this year. You've learned x squared, x cubed, you've learned square roots, you've learned rectangular hyperbolas, You've learned, what else have we learned? We learned exponential and logs. All of those, and circular functions, all of those can be used for derivative. That's why it's 2/3 of the course. Okay, and then the other third is then your probability section, but technically if you're talking about areas of study, then it's 3/4 of your course is on calculus that can be applied, and then you've got 1/4 that's left over on probability. Okay, so here we go. Once you've copied those notes, what we're going to work on today is I'm going to show you what a limit represents. Okay, so here we go. Let's have a look at, and we've already done this before, it's just I'm teaching you the notations for it. But let's take an example. Remember when you did tan graphs? Okay, so tangent graphs. I'm just going to go back to tan graphs. Remember in the unit circle, when I give you y equals tan of x, you would have had a graph that looks something like this. I'm going to just quickly draw it. We said that from 0 to pi and 2 to pi to say 3 pi and 2 there. One of the first things we realized in a unit circle, and I'm going to draw it over here. This is your unit circle. Tan represents the gradient at whatever degrees you're at, right? So at 0 degrees, this is where 0 degrees is. This is the tangent line that I have. And then I ask you, what is the gradient of this line? What's the gradient of this line right now? 0. So then we'd say, all right, so when it's 0 degrees, so x-axis is 0 degrees, then I've got a tangent of 0. So I've got my first point. As I move around the circle, the degrees increases. Okay, so it could be 45 degrees here to 60 degrees to eventually 90 degrees. As I'm increasing it, what's happening to my gradient? What's happening to the gradient right now? It's increasing, and it's positive. What's happening, though, what I'm interested in is, as it's increasing, the gradient's increasing, when it gets to 90 degrees, this gradient right here, when I draw it up, that value is becoming infinitely large, right? It's getting larger and larger and larger up until you actually reach 90 degrees, which I'll do it in a green line. What's the gradient at exactly 90 degrees? Undefined, which is why in our graph we drew an asymptote, right? And if you were to draw this, this is how your graph would look. You would say it's getting larger and larger and larger. So from here, I'm just representing what's happening to the gradient. Gradient's increasing, increasing, and it gets infinitely large as it gets closer to 90 degrees. But as soon as it hits 90 degrees, it's undefined. So at that very point, I don't have anything. What's interesting here is if I wrote it as a limit, which is what you're learning today, the language right here, so I'm just going to circle it. So that language right there, I'm just going to write it out. Limit, and they wrote h approaches 0. That lim means limit, and it just means what's the value approaching. This here is what you're looking at. So usually it's the x-axis. So in my case, this is what I would write. I'm saying that the x-axis is approaching a particular value. What am I approaching in this case here? For my tan of x, the limit that I would write is lim. So I'm saying this graph where the x value, which is the degrees, is approaching pi and 2. What I'm saying here in this notation is I'm saying what happens if I'm approaching pi on 2 for this graph when x is approaching pi on 2? What would that tend towards? When you write your answer, we know it's undefined, but technically, in reality, I'm not saying it's at pi and 2, I'm saying it's approaching pi and 2. What is the value overall? How would you describe it? As I'm getting closer and closer towards pi and 2, what's happening to the value? Increases, but how would you summarize it?
As close to infinity as possible.
Very good. And so you would answer it as positive infinity. What the exercise here gets you to practice first is how to use the concept of limit. So sometimes we don't know the actual value, but we can see it in the long term. There's a trend or there's a pattern. So we write the limit to talk about a pattern. We say that, oh, well, actually, it seems that in the long term, I'm reaching an infinitely large number, even though I don't need to exactly work out what pi and 2 is. Because if you sub pi and 2 in, you get nothing out. Well, what if I just want to know the direction of where your overall value is? What do? That's called the limit. Okay, so we use the limit to explore certain situations. So if you're doing specialists, most of you will start to play around with limits more often next year, where you're exploring an equation simply by looking at where does it approach. It sounds straightforward, but there's things to look at when you're looking at an entire equation. Okay, so now that we understand what a limit is and how to use that notation, let's have a look at what we talked about in our last session. This is my last session. We talked about curves, right? So I got a curve here. I've got a point P. This is your initial spot, X. And do you remember, if I give you a hypothetical number, let's say X was equal to 2, I said that if you picked a second point, that's the only way to find the gradient, right? You need 2 points minimum to find a gradient. Well, they're saying, what if this extra amount, now some of you from the exercise that you did, you chose 2.01, right? But we know we can get smaller than that. It doesn't have to be 2.01. You could have chosen 2.001. But if you chose 2.001, I could have chosen 2.0001. So there are infinitely many possibilities that you can write here. But the exercise that you did only chose one. And then they said that that's the estimate of the gradient at, and I'm going to use a ruler. So this is the tangent line. So a tangent line is a straight line that touches one point, and this particular point is this one, right there at P. I'm touching that point, and I want to know what the gradient of this tangent line is, right? First principles, or the derivative, every time you do the derivative, no matter what rule you use, that's what you're looking for. You're looking for at 1 point. Rather than 2 points, you're looking at 1 point. So what's first principles? I said, well, if everyone can keep choosing an infinitely smaller value, what's the difference between these two? It's h. See, from 2 to 2.001, or 2.01, or 2.0001, there's a difference of how much you're adding on. I'm adding on h amount, right? So that's why they called this, if this was x, then this would be x plus h. That's the amount that you're adding on, right? Now everyone can choose a different h value. Someone could choose 0.01, someone else can choose 0.001, someone else can choose 0001. So that h is the difference that you're making. Now the theory is, well, what if when you're finding, remember when you're finding the gradient, how do you find the gradient again? This is what you would do. You'd say y2 minus y1 over x2 minus x1. That's your gradient, true? So, according to what we just wrote, say we don't know what h is. Okay, we don't know what h is. I'm just going to delete that bit. We don't know what h is. But what we're going to say is to find out this value, or the gradient, you would do y1. So here we go. So y2 minus y1. This is my y1. This is my y2. y2 minus y1. So you got f of whatever x plus h is. For those who are confused, f of x plus h just means if this is x plus h, you'd sub that into the function, and that's how you get your y value. So if I get y2 minus y1, y1 was f of x, all over my x2, which was right here, x plus h. So here we go, x plus h, minus my x1, which is over here, x. That should give me the gradient. All I'm doing is I'm taking y2 minus y1, x2 minus x1. True? So, if we simplify this, you can see where the formula that you wrote down, or I asked you to write down, starts to come about. You then have f of x plus h, whatever that second y value is, minus the first y value, over, now x minus x cancels out, and you get h. This is what first principle is saying. We know from exercise 16D that the point you choose, the second point, the closer you choose it to the initial point, the more accurate that gradient would be. Now you could have chosen 0.01 difference, 0.001 difference, or 0.001 difference, but what if you can make it infinitely small? on a hypothetical sense. This is what first principles are saying. So first principles transformed this and said, well, if that is to find the gradient, what if I said, hypothetically, we do the limit? What if h is infinitely small? I'm not saying it's 0, but I'm saying it's infinitely small. I'm making that h value that you're all choosing, instead of 0.01, instead of 0.001, instead of 0.00001, what if I made it infinitely small? But not 0, so it's not 2 plus 0, but it's 2 plus a very small, infinitely small number. What would that be? So with that idea of limits, this is what they're saying. They're saying find h when it's so small and you still find f of x plus h minus f of x. What does this become? Because whatever that is, that must be the gradient. But the notation that they're writing, they write it as f dash of x, because it doesn't matter what function you have, this is now going to be the gradient of that function at any particular instant point. That's what it's trying to describe. So when you wrote down this formula, that's what it's describing right now. So if I rub all this out, can you see that relevance? That's all they're trying to say. They're just trying to say the gradient at any particular point you're interested in, where h, which is the second point that you're choosing, what if h was so small, y2 minus y1 over h, what does it become? Yeah.
I don't know if this is stupid, but like
No.
f of x plus h minus f of x, would that just be h?
No. So I don't believe in stupid questions. That's actually a really good question here. The reason why this feels a bit foreign is because we need to understand that as a function. And say f of x was equal to x squared, right? Then f of x plus h is not just x plus h there. What you're actually doing is you're resubstituting, instead of x here, see that's the x that you have, I'm replacing that x with x plus h. And so if you expand that, let's work it out. This is f of x plus h. This is f of x. If you subtract them, what you're having is x plus h squared minus x squared. But we know that we have to expand the brackets. If you expand the brackets, it becomes x squared plus 2xh plus h squared minus x squared. And you can see you can't cancel out that h. Yeah? So that's why what you're asking is actually a really good question. Most students do think that just cancels out, and it's not. It's what you're actually doing is you're saying, depending on what function you get, you're substituting x plus h in to replace that x. And this is where it gets tricky. Depending on what functions you get, it can be huge. Most of the time in exercise 17A, you're going to get a quadratic or a cubic function. And you have to expand and simplify, which is why the questions I've selected for you limits that. I only got you to do 17A, just 7 and 8 to do with limits. The only part you're using first principles is here, because then it limits the amount of craziness that you're going to be doing. I just want you to understand the theory. Okay? So, now, after you got the theory, that's quite a bit to take in. Let's now practice limits. Okay, so I need you to think in terms of limits, and then we'll do one example of how to do the derivative of x squared plus 2x, and then the real hard part, which I'll do it in Wednesday's session, I want you to really interpret, once you've found the derivative, what does it actually mean? Because that's what students find hard to understand. They'll be able to find the derivative, you'll learn shortcuts to do it, but you'll miss out on the understanding of what it is. And that's what my role is. My role is to change that so that you understand what a derivative actually means. And once you get that, the chapter's really straightforward. It's a very easy topic. It's just the fact that I think the understanding behind it that makes it tricky. Okay, so let's do this. Example 4. Yep.
Can you change it? There's like a bit.
Sorry, I didn't see that too. All right, here we go. Let's do this together. So the first question in 17F and 17A, I just want you to work with understanding how to use limits in your notation. Okay, so question example A. Let's have a look at example A here. Example A, you've got limits of h approach 0, and you've got of, notice I'm using the brackets here, so we're saying the limit of 22x squared plus 20x times h plus h. Okay? Now, the idea is about analyzing what happens overall. Okay, so let's think about it overall. It's all on a theoretical point here. This is H. We're saying, what if H became infinitely small? We're not saying it's 0. We're saying it's infinitely small. If you have a look at the first term, 22 times x squared. Does it matter if H gets really small? No. This has everything to do with x. So that means 22x squared will stay the same. But on the other hand, the second term, you're adding on 20x multiplied to h, and we're saying that h becomes a very, very small number. Now let's think about it. If you took number 10 and you times it by 5, or you times it by 4, or you times it by 3, you times it by 2, what's happening to the number? It's getting smaller. So if you thought about it, if you got 20x, which I don't know what the number is, but I know I'm timesing it by an infinitely small number, what do you think this overall number will approach?
0.
Approach 0. It gets very small. So infinite. We're not saying it's 0. We're just saying it becomes infinitely small. Okay, so I'm going to write here, infinitely small. That you can almost say it's 0, but it's not 0. It's infinitely small. Yeah.
So would it just be like 22x squared plus h?
Oh, that's another good question. Yes, so it's 22x squared plus infinitely small plus, now this third term, h. Now h is going to be approaching an infinitely small number. So if you're adding on an infinitely small number, what's the overall result approaching?
0.
Not 0. Well, this one is approaching 0, so it's like adding on a 0.
Yeah.
This is like adding on a 0. But what's the overall answer?
22x squared.
Yeah, because 22x squared plus infinitely small plus another infinitely small, we can estimate that an overall, it should be quite close to 22x squared, especially if you can imagine that this continually gets smaller and smaller and smaller. Then what's the overall value? We can then say it's about 22x squared. Okay, so this skill here, what we're doing here is predicting. We're not saying it's exactly 22x squared, but we can predict in the long term, in the infinite long term, that's what it approaches, which is what probability and chance is like. When you're talking about flipping a coin, if each and every one of us had 10 goes to flip a coin, it's not that all of us are going to get 5 tails and 5 heads. Some of us will get 2 tails, some of us will get 10 tails or 10 heads. But the point is that not everyone's meant to get 5 tails and 5 heads. But in the long term, though, so in the long term, which we do that statistically, yes, it will even out the plane that you end up getting about 50-50 in the larger sum scheme of things. That's the idea of limits. So right now we're doing limits with functions, and your skill right now is to solve these problems. Now they are going to come with challenges, so I'm going to show you a challenge. Let's look at B. So A was pretty straightforward. It was just one nice line. Let's have a look at B. Why is B different to A? So I got again, limit. H approaches 0, but this time you have a fraction. Now out of curiosity, when you have a fraction, what's one of the first things that you're worried about? Why? Very good. One of the problems that we are concerned about is that when h is 0, if you just thinking of it as it's just sub-0 here, sub-0 there, sub-0 there, the problem is you end up with 0 over 0. What's the answer? So then you can't figure out what it's approaching. So there are problems with these techniques, and though we understand it theoretically, how do we solve that? So this is what we do. One of the techniques, and in your exercise books, they will make questions that are more doable. So in this case here, your tip is to get rid of that fraction. That denominator is a problem. Okay, so what we do is we try to rejig it in some way so that we can interpret better. And one of the nice things is you can simplify the numerator. How do we simplify the numerator? Can anyone see? What can you do to simplify the top line? You can cancel out the h, but before you can do that, you have to take a step, which is factorizing. Okay, so you can just do that. The problem is a lot of students don't know why that actually happens. The reason why you can actually do that is because you're skipping a step. what you're actually doing is this. You're taking out h as a common factor. That becomes 3x squared plus 2 divided by h. What you're then actually doing here is you're doing h divided by h. That's why you can cancel them out.
So, but it's h squared. So that's good.
Where's h squared? Oh, thank you. Very good. Okay, so what you're actually doing, you can't just cancel the h's. It's the understanding it's factorizing. Now, once you've done that, h divided by h we know is a value of 1. Notice that I'm still keeping my notation as limit of h approach 0. Okay, don't just disappear because they will penalize you. If you're working out the limit and you haven't actually solved what it is, you leave it as it is. Okay, don't just disappear. So that shouldn't disappear. It should always be there until you've made a prediction of what it is. So here, I should have 3x squared plus 2 times h. And I'm just going to add this one down. Get more space. Here we go. Enter, 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 enter. Here we go. Now we can predict. Now we don't have a denominator to worry about. If h approaches 0, obviously the first term doesn't matter. That doesn't have any h's. It doesn't get affected. It will still stay as 3x squared. But I'm plussing on if 2 times a very, very small number, what does that overall become? A very small number. So if this is a very small number, what does your overall result become? And that's how you would do this particular problem. You would say it is approaching, or essentially it is almost equivalent to 3x squared, providing that h becomes infinitely small. Okay, so that's what you're doing in the first part of the exercise. I wanted you to have a look. What about D? Out of curiosity, what do you think the answer is then? So I'll zoom in for D. Very good. So most students will put 0. So if you don't understand what I was describing, you will put 0, or you don't understand how to approach it. That's what I was teaching to some of the year 12s that I don't teach. It's just to understand what the idea of limit is. Okay, and the idea of limit is just analyzing when a value gets smaller or large, what happens. Okay, now I haven't taught you that you can observe it from a negative perspective or a positive perspective. That's for later. At the moment, I just need you to be able to understand how to write it and how to work with these type of questions. Okay, so exercise 17A, these are the questions I want you to practice. And exercise 17F, that also is there too. Oh, sorry. So 17A, you got 7 and 8. 17F, you got question 1. That's to practice. It doesn't have to be 0. What happens if it approaches 3? What happens if it approaches 6? It's your prediction of what the overall value becomes. Okay, so that's the first step of derivatives. Okay, so I'm going to give you, it's currently 2:29. I'm going to give you about 20 minutes. Have a go with some of these questions in terms of just finding the limit. That's all I want. Once you've got the idea of limits, then I will work with you to show you an example how to find the derivative, which means the gradient at one point. Okay, so I'll then teach you how to find by first principles. Okay, here we go. This is just for